Like I said in the last slide, we use the Frost cycle to explain why fully conjugated systems like benzene with a 4n plus 2 pi electrons have exceptional stability. And you can use the Frost cycles to determine the energy diagrams for the bonding molecular orbitals and the anti-bonding molecular orbitals. And once you are able to do this, then you can fill in the electrons, and you will observe that aromatic rings will have aromatic compounds will have a fully filled bonding molecular orbitals. As you can see, if we did these examples here, for instance, this cyclobutadiene has 4 electrons. You can see we have 2 unpaired, so it's going to be anti-aromatic. You see? Now this has a total of 6 electrons. So you can have like that. So it's going to be filled. And this of course has 6 electrons. It's going to be filled. So this is going to be aromatic and all that stuff. So you can use it to be able to determine why if the molecule is going to be aromatic or non-aromatic. So let's look at the criteria for being aromatic. For a compound to be fully aromatic, right? First of all, it has to be fully conjugated with overlapping p orbitals, meaning that it must be planar. And the second thing is that it must meet the Huckel rule, which states that an odd number of electron pairs of 4n plus 2, where n is equal to a whole number. So it's either it has an odd number of electron pairs, or it has a total number of electrons of 4n plus 2. Now, anti-aromatic compounds fulfill 2 criteria: a fully conjugated ring with overlapping p orbitals and an even number of electron pairs, or 4n total pi electrons, where n equals 0, 1, 2, 3, 4, and 4. Okay, so notice that with anti-aromatic compounds, even though they may be fully conjugated with overlapping p orbitals, they have an even number of electron pairs, or they have 4n total pi electrons, where n of course is a whole number, or 0. Okay, so make sure you know the difference between the two, right? Now, aromatic compounds other than benzene. Now, annulenes are rings that are fully conjugated. So, aromatic compounds fall into a class of compounds that are called annulenes, right? In this case, you have an annulene with 6 pi electrons. Here you have an annulene with 10 pi electrons, and here you have an annulene with 14 pi electrons. And all these are considered to be aromatic because they have an odd number of pi electron pairs. Okay, and that makes them aromatic. Now, some annulenes are aromatic while others are anti-aromatics. Now, alunita is neither. The reason is because it's not planar. So this is not aromatic, even though it has 10 electrons, right? But because it's non-planar, right? Because it's non-planar, it is considered to be non-aromatic. Okay, it's considered to be non-aromatic. So in addition to cyclooctatetraene, which is non-aromatic, I want you to know that annulene or 10 annulene, which has a total of 10 electrons or 5 electron pairs, is considered to be non-aromatic. Okay. Now, aromatic compound other than benzene, some must carry a formal charge to be aromatic. If you consider something like a 5-membered ring like this, so for instance, this is the cyclopentadiene, dinyl anion. You see it has an anion here. So you see, because it's an anion, it has a total of 6 pi electrons, which of course satisfies the 4n plus 2 rule, where n equals 1. Or you can say it has 3 pi electron pairs. And because it has 3 pi electron pairs, of course it will be considered to be aromatic. Okay, and of course you can see how that negative charge can be delocalized over the entire ring using resonance structures. So these are the resonance structures, and of course this is what the hybrid is going to look like. Okay, now we have evidence for this, that this molecule or this anion is exceptionally stable. And the reason why it's exceptionally stable is because it's aromatic. Okay, it's aromatic because it's exceptionally stable, and the reason why it's exceptionally stable is because it's aromatic. You see, so you can see here the equilibrium favors the right side, and that's because it's exceptionally stable because of the fact that it's aromatic. As you can see here, it has 6 pi electrons, right, and n equals 1, and also it has 3 pi electron pairs, and as a result it is considered to be aromatic. Okay, it's considered to be aromatic, and that gives exceptional stability. And that's why when you're looking at the acidity of this proton is actually way more acidic than the proton on an alkane. See, here we expect the proton on the alkane to be pretty similar in acidity to the proton on the cyclopentadiene. But the interesting thing is that this is way more acidic. In fact, it's 10 raised to the power of 34 times, after 24 times, sorry, 34 times more acidic. You see, this is more acidic than this. You see, than the alkane. You see, and the reason is because once this proton is lost, once you have the proton transfer, it forms an exceptionally stable anion, which becomes aromatic. And because this is really stable, the conjugate base is very stable because it's aromatic. You see, the conjugate base is very stable because aromatic, and so the equilibrium is going to lie towards the right. Okay, it's going to lie towards the right. Now, the same is also true when you look at the cycloheptatrienyl cation. You see, when you look at the cycloheptatrienyl cation, you can see that here you have 3 pi electron pairs. You have 3 pi electron pairs, right? And again, the total number of electrons, which is 6, is equal to 4n plus 2, which is 6 pi electrons. Yeah, so even though it has a charge of positive, right, it still has 6 pi electrons, and you can see how we can delocalize the pi electrons all across the ring. So there is a continuous overlap of unhybridized p orbitals, and that makes the molecule, the cation, sorry, very, very stable because it's aromatic. Okay. Now let's look at aromatic compounds other than benzene, especially those that possess heteroatoms. For instance, if you look at pyridine versus pyrrole, pyridine is way more basic than pyrrole. It's actually a moderate base. It's a moderate base, while pyrrole is a very weak base. So it's a weak base, and the reason is because pyrrole can become aromatic And the lone pair of electrons, these electrons actually participate in resonance. As you can see here, if it draws resonance form, you now have a total of 3 pi electron pairs. Okay, you have 3 pi electron pairs, and also you have a total of 4n plus 2 pi electrons. Okay, because 4n plus 2 is not equal to 6. If you look here, you have 6, and where n equals 1. Okay, and so because pyrrole is can become aromatic by utilizing these 2 electron pairs here, this electron pair right here, it can become aromatic. You see, it's a very, very weak base. It's a weak base. Okay. On the other hand, pyridine is already aromatic, and so this lone pair of electron does not participate in resonance, and so it can be utilized as an electron source, making it a moderate base. Okay. So if the heteroatom's lone pair of electrons is necessary, it should be included in the Huckel number. But in this case, it's not necessary. This is not necessary, and so this can be react as a moderate base. However, this is necessary because it can be used to make it aromatic. Okay, can be used to make it aromatic, which we saw in the previous slide. See, so this electron pair in the unhybridized p orbital can be used to help pyrrole become aromatic, and because once it becomes aromatic, then it becomes exceptionally stable. Okay, now if the lone pair is necessary to make it aromatic, the electrons will not be basic. Of course, that makes sense. But in this case, the lone pair is not necessary to make it aromatic. Not necessary. And so, because the lone pair is not necessary to make pyridine aromatic, pyridine is actually a moderate base. It's a moderate base because the lone pair is not necessary to make it aromatic. On the other hand, when you look at pyrrole, pyrrole is a very, very weak base. This lone pair of electron is not available. It's not available. The reason is because it is used to help the molecule become it's used to help the molecule become aromatic. You see, it's used to help the molecule become aromatic, and so because it's a very weak base, even if it were to pick up a proton, it's going to make a very, very strong acid which is non-aromatic, and so the equilibrium is going to lie towards the left. It's going to go backwards. You see, it's going to lie towards the left. Okay, so I want you to look at that distinction. Look at pyridine and look at pyrrole. You can see that pyrrole is a very, very weak base. That's because the lone pair is necessary to make it aromatic. On the other hand, pyridine, which is right here, is a moderate base because the lone pair is not necessary to make it aromatic. And so I want you to make a note of that. The difference in electron density can also be observed by viewing the electrostatic potential maps that we should talk about. For instance, pyridine, you can see here that the electron pair is not necessary to make it aromatic, while here the electron pair is necessary to make it aromatic, or the electron pair is delocalized, and so it acts as a very weak base. Very, very weak base. Okay, all right, now these are just some examples. You can see that this has a total of 8 pi electrons, and so it's anti-aromatic. This, after you join resonance, has a total of 8 pi electrons, right? It's non-aromatic because it's not planar. Okay, here this has a total of 10 pi electrons. It's aromatic, but it could be non-aromatic as well. That's in case if it is non-planar, right? While this has a total of 8 electrons, and it is considered to be anti-aromatic. Okay, because it has 8 electrons. And these are some more examples which help us to see the ones that are aromatic and the ones that are not